introduce Emmanuel Schanzer. Emmanuel is a creator and co-director of Bootstrap, one of the largest formal K-12 computer science initiatives in the US. He spent several years as a program manager and developer before becoming a high school teacher and middle school academic coach, and has long been involved in connecting educators and technology, building partnerships with professional organizations, universities, and companies from across Silicon Valley to bring rigorous, high-quality CS education to all students, particularly underrepresented groups. He holds degrees in computer science and curriculum development, and his research focus involves using programming to teach algebra.
Cool. All right. Well, thank you. Well, hi, everybody. Oh, thank you. Thank you. I haven't even started. So I want to thank all of you for being here today. And also, as I mentioned before, I really appreciate you taking a moment away from the Comey testimony to join us here. So it's great to be back at Google. So thank you for having me. I especially want to extend a thanks to Andrew for the invitation, for setting this up. And I'm going to spend the next 35 or so minutes talking to you about computer science education formulated as an engineering problem. So as Andrew mentioned, my name is Emmanuel. I work with a team. Their names are up here on the slides: Shriram Krishnamurthy, Kathy Fissler, and Emma Yunsmith. And Bootstrap right now is one of the largest formal in-school programming courses in the country. We reach about 20,000 students every single year. Most of these students are taught by teachers with little or no computing experience. 43% of our students are girls and young women. 46% self-identify as African American or Latino. So if you're counting these numbers, these are pretty good in the CS education business. A lot of these classes often struggle to recruit underrepresented groups. I'm going to tell you a little bit about how we did what we did, where we're going, and hopefully pass on some of those lessons to you guys, especially since you were engineers. And I think this is a problem that you guys have a unique way of looking at. And engineers broadly, also sales, geos here as well, I guess geo engineers, but Googlers overall. So let's start with a question. Somebody walks into your office and says, I want to teach computer science. You guys are the expert. You work at Google. So what language should I use? So I'm just curious. Take a second. I want to hear like a couple of suggestions. Like three folks. What would you recommend to someone who's asking you this?
Scratch is a good one.
Excellent. Scratch. What else? Python. Great. One more.
I recommend Lisp.
He recommends Lisp. Great. OK. There's always one. All right. Sounds good. And this, in fact, is exactly the way it goes. So here's an example of an actual Facebook thread. Someone posts and says, hey, I'm looking for advice on teaching some coding. What do people think I should use? And the responses are all things like Scratch, indeed, was the first one. Someone else is recommending some logo. Someone else is looking at, let's see. They're talking about maybe C++, maybe Java or Python. So the answers are all immediately, here are some languages, here are some tools. Let me ask you a slightly different question. Someone walks into your office and says, hey, I want to make software. You guys are Googlers. What language should I use? So what do you tell them?
No, you ask what type of software.
So you would push back. You'd say, well, what kind of software do you want?
Like if it's an Android app, you have to use Java. If it's an iPhone app, you have to use C, Objective-C or Swift or something.
Yeah, so you're saying that maybe before you answer with the language, you would ask a little bit more about what this person's trying to make. Right? Even though they came to you asking for a language, you're saying, well, back up a second. What do you want to do? And I think that's sort of telling. That when someone asks an engineer, what language should I use, the engineer says, back up, what are you trying to do? But when it comes to education, if a teacher says, what should I use, we're instantly quick to jump in and say, you should use C#, you should use Scratch, things like that. Why? I mean, as engineers, the first thing we should be doing is looking at what are the constraints of the problem. So here are some educational constraints that we should be asking before we answer that teacher's question. How old are the students? Right? Maybe they're 30. Maybe they're 5. That might change our answers a little bit. Have they had prior programming exposure? Is it their first programming class, or do they have master's degrees in computer science? Is it a required class where you're going to have every kid there, or is it self-selected kids? How long is it? Right? Is this to run at an all-day summer camp, 8 hours a day every day, or is it like a half-an-hour coding club Monday mornings? Is it even a class? Maybe it's a drop-in coding club over at the local science museum, and some kids are there every day. Some kids show up once and you never see them again. Now, I think if I had given you guys more time to think about this question, you would have come back with some of these constraints. You would have asked about them. But there are some other constraints that you might not have thought of. So if you're interested in getting computer science into an educational context, you should also ask yourselves, how many kids are there? Right? Is it one teacher teaching a giant lecture hall, or is it just a small group of kids? Similarly, is there internet access in the school or in the educational setting? Is the teacher new to programming? Maybe the teacher has never coded before. Can the students type? That is a critical question that might immediately lead you to say, well, Scratch is a great place to start if they can't type. Are there students with different ability levels, right? Are they visually impaired? Do they have sensory motor impairments? If you're talking about schools, the answer is yes, and you have to ask what those impairments are, what the different ability levels are, because those will change your answer. Do they have regular computer access at home? Because if you're teaching a programming class and you're relying on kids completing programming assignments for homework, this matters. And in fact, do they even have regular computer access at school? Right? I mean, if a teacher says, I want to teach computer science, we often think, oh, you must have a computer lab. Kids must have computers every day. Often, what it really means is there's like a laptop cart that comes around on Friday. So these are the constraints that we need to ask about before we even barge in and say, well, here's how computer science education should work. And as computer scientists, we often over-fixate on the tool. Right? We jump into the language, we jump into the software, which is why I think when you look at the last 40 years, the history of CS education is a history of tools. Here's the new tool that's going to change the way programming is taught forever. And then 10 years later, here's the new tool that's going to change the way programming is taught forever. And this endless cycle never gets us anywhere. So let's look at this as engineers and say, let's define the problem. What are our constraints and what are our metrics? We've talked about our constraints. I'm going to posit that there are 3 metrics we should consider. So first is equity, right? Without equity, we could get computer science into every school, and then the only kids who show up for the class are rich white boys. And I think none of us would be thrilled with that. So equity is number 1. We also want scale, right? We need this to be reachable by millions and millions of kids. And you've got things like Hour of Code that reach millions upon millions of kids, all kinds of kids. But even code.org, even Hadi Partovi himself would say Hour of Code is not rigorous education, it's merely exposure. What we want for our third criteria is rigor. If we haven't gotten all 3 of these, I would propose that we're never fully successful. We're never where we need to be. So with these goals in mind, let's look at the solution space. Because there are sort of 4 strategies that people tend to use when it comes to CS education. So the first is, let's make it a required course. Every child in America must take computer science before they graduate. Okay? There's a riff on this, which is, no. There should be a computer science course in every school, but it's optional. It's an elective that kids can choose. Option 3, forget all of that. We're going after school. And option 4, maybe instead we try to integrate computing into some existing mainstream classes. So let's look at these 4. And I just want to say that all 4 of these strategies have merit. So as I go through this, some have strengths and others have weaknesses, and that's fine. I think there's room in this space for a plurality of approaches. So let's start with the required course, right? Let's talk about that strategy. Well, the problem with required courses is that this strategy doesn't scale. If we really wanted to get computer science to be taught to every child in America, here we need to do 4 things. First, we would need to have something called CS teacher certification in every single state so that a teacher could become a CS teacher. And right now, less than half of the states have such a certification. So that means a policy effort that's going to take a lot of years and a lot of dollars to create. And then once that's done, we need to recruit and train at least 20,000 full-time dedicated CS teachers. And that's even more years and even more dollars. And then let's just assume that none of those teachers decide to peace out and go work for a technology company because now they can make a whole lot more money. Let's just assume they all stay in the classroom, right? We still have to pay their salaries, which means at least $1 billion a year added to the national education budget in every single year in perpetuity. That's not going to happen anytime soon. But suppose somebody with deep pockets opens them up and says, I'm going to pay for all of it. It's totally OK. Well, beyond paying their salary, there's also the laws of time and space. And there's a finite number of hours in the school day and rooms in the school building. So where are these CS classes going to fit? Right? It's essentially a non-starter. So there's a lot of benefits here, but right off the bat, we give up on scale. Right? That's not happening with this strategy. Even worse, if it's a required class that kids need to complete to graduate, That means you have wildly different ability levels in that classroom. And because it's a graduation requirement, there's a perverse incentive on the part of the teacher to get rid of the rigor, right? To make sure that every single kid can pass it, because we don't want kids dropping out of high school because they didn't pass their CS class. So we may lose some of the rigor as well.
Would that just happen in every course, is that true?
Well, I mean, it often does.
I mean, I was a teacher for the last 3 years, that's why, I agree with everything you said so far, but that strikes me as sort of a...
And that's why it's shaded, right? So some teachers will hold the line. Some teachers will say, no, I'm going rigorous the whole way.
The scale thing, I think you're 100%, I totally agree with everything you said, but I don't know, that one doesn't strike me as...
And that's why it's half on there, right? I think some teachers will take the approach that you would take. There are other teachers that are going to say, you know what? I wasn't even a CS major. The fact that I don't know, this computer science class, I don't want any kid to fail it. So we're just going to do something that's fun and sort of easy to pass. And that's merely a risk. It's not a definite outcome. So let's take a look at strategy number 2. What if computer science were simply an elective, right? That solves some of these problems. Well, the problem with elective courses is that they're not equitable. And I'll tell you why. So every school has a set of graduation requirements. So here's a hypothetical grid of courses that a student might take in different subject areas, years 1 through 4. And you can clearly see there's room for computer science there. What happens if a kid fails a required course? For example, Algebra 1. Well, then they have to retake it their sophomore year, so we've just moved this pathway down a notch. But they're also doubling up. The school will typically assign them to a second math class, like a remedial math class, to make damn sure that that kid passes their algebra class this time. And of course, they're missing their 4th year of math, so what happens? They get another year added somewhere else in a different track, maybe financial math, applied math, something like that, to give them the credits that they need. And then over on the science column, you'll notice that virtually every science has algebra as a prerequisite, right? Without algebraic functions, you're not modeling projectile motion in physics. You're not balancing chemical equations. So often there's a delay introduced, a bubble in the pipeline. And that's if they fail class once. What if a kid fails 2 classes, right? You had this nice grid structure that allows for all these courses, but now there's this cascade of errors. That means that these students don't have room in the schedule to take the electives. So for students who fail these classes, they're X'd out of these options. And when you look at the students that typically struggle in the mainstream classes, often they split along class lines, poverty lines, SES, and because of some structures that we have in America, those are also divided among racial lines. So these elective courses are great to have, but it's no surprise that when you look at the courses that are being offered right now as electives, often there's a particular profile of student who winds up being in the classroom. So going back to our scorecard here, we lose equity off the bat, and I think that there is often something of a risk in losing rigor, and I'll tell you why. Because for a school that's just offering a single computer science elective, it's not cost effective for them to hire like a full-blown computer science teacher. So what are they going to do? Who's going to teach that class? Maybe a math teacher, maybe a history teacher, right? They'll ask another teacher to take over that class, which means we lose the ability to ensure that they have the necessary training and depth of content to ensure rigor. So again, rigor is sort of a risk here. So let's take a look at strategy 3. What if we just bypassed the schools altogether and did computer science as an after-school program? Well, this is a strategy that I can tell you a lot about. So Bootstrap began as an after-school program. And several years back, early in our growth, we were actually one of the largest after-school programming curricula in the country. And in fact, we had tons of engineers from Google who taught the class in after-school programs. And when we looked at the impact we were having, we shut it down. That's a battle scar, and I'm going to tell you my reasons for doing so. See, the problem with after-school computer science is that, by definition, it has to compete with after-school football, basketball, theater, sculpture, having a job, taking care of your little brother, which means the only kids who show up for after-school CS are the kids with the means and inclination to do so. They already see themselves as interested in coding. So equity goes out the window very, very quickly. Once you scale beyond a certain group, you lose equity. But there's something else, which is that after a long day of school, kids are exhausted, justifiably so, which means it's extremely hard to teach a rigorous after-school programming class. Now, this is not to knock after-school coding clubs. I think they're fantastic. I think they add a lot of value. But I think often the critique that you hear is, this after-school thing, it's really great, kids are getting engaged, but I wouldn't say they're learning rigorous computer science. So easy to scale, but you risk losing some other stuff as well. So we've sort of ruled out the first three strategies as having some benefits, but not necessarily getting us to all three of our metrics for success. So I want to pause for a second and give you an inequation. The idea that everyone should learn computer science does not mean everyone should take computer science classes. I think this is a tenuous connection that we need to sever. So I want to talk about the fourth strategy, which is what does it look like to integrate computing into a mainstream course? And if you were to pick a course, any course, I think you'd want to pick algebra. And I'll tell you why. So first, algebra is the gateway to all STEM. As I mentioned before, you fail Algebra 1 and you just give up on math right there, yeah, you're screwed for the part of STEM, right? You're not going to become a mathematician. But you're also not going to become a physicist without functions. You're not going to become a chemist, a biologist. Even if you want to go into economics, financial literacy, you need to know algebraic functions if you want to model things like compound interest. So a kid who flames out of Algebra 1 has essentially made a career decision where they're X'd out from STEM. In fact, this impact is so significant that a 2004 study looked at the correlation between grades kids get in high school and their lifetime earnings. And what they found was that the grade a child gets in Algebra 1 is the most strongly correlated of any subject with the amount of money that child will make for the rest of his or her life. And finally, we live in an era of high-stakes testing and standardized tests, and Algebra 1 is a requirement in every single school in the United States, which means that the superintendent of New York City public schools isn't staying awake at night having, shivering, saying, why aren't my kids learning to code? What they're really worried about is, are my kids going to be able to pass the algebra exams? And this is happening nationwide, right? Typically, when you hear people compare how we're doing to other countries, the thing that scares us the most is other countries are beating us in math. And guess which part of the math test people freak out about the most? It's the algebra. It's the word problems.
What about the geometry? Just curious.
I mean,
Or is that not required everywhere?
Not only is it not necessarily required everywhere, but typically when you think about Americans who are scared of math, it's always the train leaving Chicago and the train leaving New York, right? It's this like nightmare word problem that we all giggle about, right? Because it's true, we have like national PTSD when it comes to algebra. So this is a class that's in need of help. So what if we tried to teach computer science through the algebra class? What if we integrated? So I'll make a strong claim here that the integrated strategy is scalable, equitable, and rigorous. Here's why. It's scalable because every child takes algebra, right? You're immediately reaching every child in the country. You're leveraging the huge network of existing teachers, courses, and professional organizations that are already out there. So we can grab that scale and run with it to teach computer science. It's also equitable. You know why? Because everyone takes algebra, which means right off the bat, you're removing the negative stereotypes that are accidentally reinforced by things like electives and after-school clubs, where when other kids look at who's taking those courses, they say, oh, that student doesn't look like me. But if you're in the algebra class, we get rid of that right off the bat. We're all in it together. And it's also fairly rigorous, right? The content in algebra is well suited to rigorous instruction and evaluation. Algebra teachers confront issues of abstraction and formal notation all the time. There are some great corollaries here that we can put to use to teaching computer science. So you're probably sitting here saying, oh my God, Emmanuel is telling me that this is basically a free lunch, right? We get all of those metrics for free. It's fantastic. Do you believe me? No, because there's no such thing as a free lunch. So here's what we do. Right? We've essentially traded one set of challenging constraints for a different set of challenging constraints. So rather than trying to jam computer science into a resource-starved educational context, now we have a different constraint problem to solve. If we want it to fly, we have to have transfer, which means the computer science kids are learning in the math class had damn well better result in them learning math better than they did before. Otherwise, the math teacher is just going to revolt. They're going to say, I don't care how cool this is or how useful it is. My job is to teach math. And if I'm giving up time from my math class, it better result in improved math outcomes. Right? So in cognitive science literature, this is a phenomenon called transfer. Transfer is pretty simple. A skill learned in one context can be used successfully in a different context. That's our goal. And it turns out that transfer happens all the time, but almost never in the way you expect. If you want to actually guide kids to transfer, it's much harder than you think. So how do we guide kids from transferring skills in computing into algebra? Well, we know that there are 3 new constraints. Number 1, you have to have explicit instruction. Having a kid perform task A and then later having them perform task B, A and B might seem similar to you, but you have no guarantee that student is going to make the connection. And often, without having a teacher in the room to explicitly tie the two together, it ain't going to happen. But that's OK, right? We're dealing with math teachers, so we can check that one off. Whew. Number 2, the tasks that you're using in domain A and B have to have deep structural similarities. How deep am I talking about? I'll give you an example from a 2009 case study. They looked at a physics teacher who was talking about gravity and acceleration and had his students do tons and tons of problems where a ball was dropped off of a tower or off of, out of an airplane, things like that. And they studied how fast the ball was moving after a given time, where it was after a given time, all sorts of stuff. And then they gave the kids a quiz. The quiz had balls being dropped down holes. And the students complained. You know why? You didn't show us any hole problems. So this level of structural similarities needs to be insanely high in order to really facilitate transfer. And finally, you need to have a process for performing tasks, right? You can't just give kids a problem in domain A and then assume that they will magically understand how to transfer that to solving that problem in domain B, right? A classic formulation of what I just said is we often think that we're teaching kids problem solving simply because we give them problems to solve. And that's not true. So we've got to have an explicit task. So these are our new criteria. We've already got one. Let's talk about how we get number 2. Deep structural similarities between computer programming and algebra. Well, there's a problem. Because most of the coding that we do in K-12 doesn't actually have functions. And functions are kind of important for algebra. So a lot of teachers will use function machines, right? There's inputs and outputs. There's a vertical line test. Except often you have functions that return void. Or functions that you give them the same input 10 times, you get 10 different outputs. This is perfectly common in many programming languages. There's no computed output, right? Here's a block from a language you might be familiar with. What's the output of that function? There's nothing computed that's showing up. So for a teacher who's trying to make connections between the functions on a computer and the functions in algebra, this doesn't fly. Coding also doesn't have variables for the most part. Here's a classic example from Python. X equals 10. And now x equals x plus 2. When you run this program, what's the final value of x? Class? Fantastic. Actually, no, that's not right at all. I'm a math teacher. This is nonsense. And you can probably guess why. And there's actually 2 problems here. One is, well, can you guess what one of the problems is?
There's the overloaded reading of the equals.
Yeah, we're overloading the equal sign, right? We're treating something that has a clear definition in mathematics to mean assignment, right? Assignment is not equality. So that's a syntactic problem. But there's something much deeper at work here, which is the semantic problem, because assignment does not exist in math. And for those of us who know that sometimes state can be a little bit hairy when you're writing code, right? State is a known challenging thing for young programmers to get a handle on. And that's hard in a programming course. Now we're going to ask math teachers to teach that and at the same time sufficiently differentiate it from the equality concepts that they're learning in the math book. So this is a very tall order. And it gets worse because coding also doesn't have numbers, and you kind of need numbers to do math. What do I mean by that? Well, of course, you guys know what 1 over 2 is, right? What's 1 over 2? It's 0, right? Because in Java, that's what you get. And you might say, oh, Emmanuel, you're just being silly. A teacher needs to make sure that they're teaching kids to declare things as a float, not an int. Maybe that's true, except in a math class, that's not part of the standards. And so now we're asking math teachers to teach kids about these different partial representations of numbers, which again, takes valuable time away from actually teaching math, and that's a problem. But of course, these partial representations, no matter which one you pick, you're going to get burned one way or another. A math teacher will often teach kids this important property. If I have 3 numbers, A, B, and C, these 2 expressions are equivalent. Y'all agree? What if A plus B is too big? Right? Maybe A minus C buys us some room before we have an overflow. So the bottom one computes, but the first one gives us an error. Or maybe vice versa. The bottom one has an underflow error. So this statement that these 2 expressions are equivalent is now wrong. In a math class, it's wrong. And it gets even worse because let's say we use those floats, for example. Well, floats introduce error, right? Which means that these two expressions are no longer equivalent either. We've just broken associativity and distributivity in a math class. And we're going to ask a math teacher to teach it too. Even if we could. These are known obstacles for transfer. So if your goal is teaching algebra, this is deeply problematic. So what do we do in Bootstrap? Well, we decided, you know what? Functional programming is a pretty decent way to do this. It enforces much more algebraic behavior. We chose a language that has a strong numeric tower implementation, so numbers behave as close as is reasonably possible to the numbers that behave in the book. So we get a lot of the deep structural similarities. And then we actually do programming using word problems taken from a math book. So we get some of that for free. But what I want to get back to is this idea that the takeaway should not be functional programming is awesome, right? Functional programming is necessary if your goal is algebra, but it is not sufficient. You also need a curriculum that uses functional programming, because the curriculum is critical if you want to teach the process for performing those tasks. So I'm going to explain this using an extremely scientific graph. So pay close attention. This is very, very scientific. We can graph a student's frustration level as a function of the number of lines of code that they've written. And typically, it looks kind of like this. So you give kids a programming challenge, and you say, all right, kids, solve it. So they fire up the editor, and they're starting here. They're going, I don't know where to begin. That first line of code is sometimes the hardest line for a kid to write, sometimes even for an adult. This is essentially called the blank page syndrome. They're like, where do I begin? But eventually, maybe with some prodding from the instructor, or maybe on their own, they start writing some code. They're starting to get things going. Their frustration level goes down. And students are kind of like 3D printers, right? They work by additive manufacturing. So every time they encounter a bug, or every time they encounter a new feature, what's their solution? Add more lines of code, just more lines of code. And gradually the complexity goes up, and they hit a bug, and the way around the bug is, I'll just check for that case, and I'll add more lines of code, and so on and so forth. But eventually this path becomes unsustainable. And it gets harder and harder to fix those bugs, and eventually the kid raises their hand and says, my program doesn't work, I'm stuck. This is a common pattern in computer science education. And those of us in the room who may have done some teaching of computer science may have seen some of this play out. Now, how do you deal with that? Well, let's look at any other discipline, right? Every discipline works in a completely different way from this idea. They have, like architects. Architects don't start by pouring concrete and then just adding stuff until you get a building, right? They have 3D models, they have blueprints. Let's say you're building a device. Maybe you're building the first mouse, right? You don't start by ordering a manufacturing prototype and then adding to it until it works. You probably think it through with some circuit diagrams, maybe some other kind of model. The point is, we don't just jump to the solution and start hacking at it until it works. Typically what we do is we follow some sort of multi-stage path to a solution, right? We start with one thing and then we build on it. And that one thing is not the same representation as the finished form. An architect might start with a blueprint, not concrete. So we have these multiple representations that we pass through on the way to a solution. And each representation represents a different perspective on the solution. So one representation might be great for answering one category of questions, and a different representation might be better for another category. This multidimensional view is also present in software engineering, right? Often there are specs, often there are test cases, often there are user interaction specs that are written up. There are lots of things that you go through before you just instantly start coding. And it turns out that there's a multidimensional view that every teacher, every math teacher cares about too, which is functions. Functions have multiple representations. I can think of it as a symbolic form. I can think of it as a line on a graph. I can think of it as a mapping between a table of inputs and outputs, and a mapping between domain and range. So every algebra teacher out there already understands this idea of multiple representations, multiple stages, and multiple viewpoints. So what does this look like in a programming class? So this is an actual worksheet from the Bootstrap curriculum that math teachers use. It's got a fairly simple word problem. This one is aimed at programming. So in the process of making a video game, so every Bootstrap kid builds a game, they need to write a function that controls the movement of their target. So we have our word problem. Write a function update target, which takes in the target's x coordinate and produces the next x coordinate, which is 50 pixels to the right. Step 1, contract and purpose statement. We ask students to come up with the name, the domain, and the range of that function. and to write a purpose statement, an English language summary of what that function does. And then we ask them to write some examples. Update target given 10, the work it should do is 10 plus 50. Same thing for 20. Then we ask students to identify the pattern. What's changing? What's the rule? And from there, they can derive sort of the finished form. Now, as software engineers, this looks somewhat familiar to us, right? That first stage kind of looks like having them write a type specification, and maybe a comment as well. That second part looks an awful lot like writing test cases. And then, of course, the final representation is then you go and write the code. So students are doing all three. A math teacher would totally disagree. A math teacher would say, no, 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 no. That first step, I know what that is. It's domain and range. It's thinking of a function machine as mapping between these two sets. And that second one, that's input-output tables, right? That's that little, the t-table, mapping between discrete input and output pairs. And finally, I don't know what that code thing is, but this is clearly the symbolic form of a function. So these representations dovetail beautifully in the context of a math class. So we've got multiple representations of code, multiple representations of functions, and with this as a scaffold, we're able to manage this frustration. Because at every stage, students know what's expected first. The very first thing I do is write the contract and purpose statement. And each one of these gives you a different perspective on the problem, a different viewpoint, which allows you to build into the next stage. So scaffolds are useful. This is the explicit task that teachers teach students how to do when they're programming a computer that they can then transfer over to the domain of math. When I'm working on a word problem, I'll use the same strategy. So when you look at things this way, we sort of have a dependency graph if we want to satisfy these constraints. So there are three things at work here. You got to know what programming language you're teaching. If you want to teach computer science, what language am I teaching? You also need to have a curriculum. How am I going to teach it? Right? What activities are kids going to go through? And then you need a pedagogy. What will it look like? What is the explicit task that students are learning? And often we just pick one off the shelf and say, we're teaching Scratch, great, now let's build a curriculum. We're teaching Python, great, let's figure out a pedagogy. But can you guess what the dependency graph looks like here?
Probably pedagogy first.
Well, pedagogy first, anyone disagree? If we were to draw arrows here, where do they go?
I mean, it seems like if you're choosing language first, you're going to choose Scratch.
If someone says, I'm going with Scratch, they would choose language first. But let's say that you're starting from a clean sheet of paper. We want to change CS education. We want to set up a class or an after-school club or a whatever. What does the dependency graph look like here? Is there a dominator? Are they codependent? What do you think?
I would say language last.
Maybe language last? Well, you can approach it from any perspective, but all three of them have dependencies on each other. The moment you make one choice in this graph, you instantly prune the tree for what you can do elsewhere. So here's what we did to build a curriculum that could be integrated into a mainstream algebra class. So I heard a volunteer say maybe we should start with the language, so sure, I'll start there. We knew it needed to have easy unit tests, right? It needed to be really trivially easy for kids to create that input-output table. So that meant for us, vertical line tests. We really wanted a functional language so that we wouldn't have to manage state. We also wanted first-class images because images are engaging and fun, and it's really nice if kids can just write some code and see the output right away as a computed output from the function, rather than worrying about setting up a buffer somewhere and then retrieving it. But most importantly, we wanted mathematical semantics. We wanted to have that deep structural similarity between tasks.
Something to add on the images thing is one of the main reason kids are scared of the math class is, well, they were scared of the previous math class and the previous math class before that. But what the kids think math is arithmetic. And as soon as they see numbers, their palms start sweating. So when I've taught this kind of thing, we start with images on the first day of class, and we get to numbers about week 3 or 4.
Mm-hmm. Yeah, so making images easily accessible, lowering that barrier, for some kids can be a huge motivational boost. So these were the criteria we wanted that led us to choose the language we wanted. And I just want to point out, we started with the criteria, not the language. We started with those 3 things, and from there we picked our language. We didn't decide we were in love with Lisp and we wanted Lisp, for example. But for our pedagogy, we used structured problem solving, right? Because we wanted to get that explicit task. And that problem solving strategy had to be multi-representational. It had to use worked examples because that's the pedagogy that math teachers are familiar with. And we actually borrowed it from a phenomenal program that's been running for more than 20 years at the university level called Program by Design. So it's an effective pedagogy that's been proven successful. We ported it to middle and high school math. And then finally, you need a curriculum. And by the way, for those of you that are interested in teaching computer science, maybe at a local school or at a summer program, a curriculum is not a list of activities. That is not a curriculum. A curriculum involves lesson plans, homework assignments, exit slips, warm-up activities. It's aligned to national and state standards so that a teacher knows where things fit. If you're expecting that teacher to go and build this on their own, looking at a list of activities, it's not going to fly because guess what? Teachers are really busy. And the curriculum we developed has a narrative final project that ties together everything students have learned. Every student in Bootstrap builds a video game of their own invention. And so at the end of the class, kids can do a video game launch party. Right? It's sort of like a science fair for the math department, where they show off what they built in their math class. We believe that algebra is the moment where math becomes creative. Right? You're literally making your own functions. You're building your own mathematical tools. Well, let's make a video game out of it. And so you'll notice that what kids are presenting here is not showing off their cool graphics for their games, although they do show that. We actually have kids do code reviews. Parents, friends, teachers, and sometimes visiting engineers ask students questions. Why did you do it this way? What would you have to change to add this feature or that feature? And students are required to look at which representation makes the most sense to answer that question. Is it my unit tests? Is it my type specification? Or am I going straight to the code? So this is something that we're doing at the middle and high school level because we're building on something that math teachers already have them do. Kids are used to going up to the front of the room and explaining their solutions. So that's what we do at Bootstrap. That's the strategy that we've taken. And we believe deeply in equity, scale, and rigor. And we can do this not just through algebra, but also through additional curricular offerings. So we've partnered with the American Association of Physics Teachers to build a Bootstrap physics module that does the same thing for a physics class that we've already done for algebra. And we're also working on a data science module that can be integrated into a high school statistics class, or there are plenty of other classes that use spreadsheets, right? Business classes, civics classes, right? There are students who might want to ask, I think stop and frisk is racist, or I think it's not. And guess what? That database is publicly available. And in the data science curriculum, teachers can have students answer that question themselves by viewing programs as questions they ask of data. And by aligning it to the standards that teachers already have to teach, we can embed this in a mainstream class. Our vision is that a school should be able to give kids at least 3, if not more, entryways into computing throughout their high school career, all without having to find room in the budget for a new teacher or room in the schedule for a new course. If you want to get involved, there's tons of things that, there's tons of places to help out. We build compilers, we create programming language, we live on the web. All of our stack is built on Google technologies. So if you're interested in helping out, but you're like, I kind of want to focus on the engineering side, there's a ton of engineering help we could use. If you want to be an advocate, talk to your local school or district. Ask them why their math teacher isn't using computer science when they could. Spread the word at the office. And of course, if you'd like to contribute, you can. Our website is here. I want to end on this note. I think Google, more than any other company in the world right now, understands the importance of disciplined, sometimes unsexy engineering. I mean, you guys have thousands of engineers working on data integrity, right? Just to make sure that one file doesn't get corrupted when it's duplicated, across the network. Users don't often see the magic that's going on there. But Google understands that that kind of stuff is critical for building a scalable infrastructure. So often in the tech sector, when we approach education, we stop thinking about it as an engineering problem. We just dive into what we were taught, what we think is cool, what we think kids will enjoy. We lose the engineering side of things. This baffles us at Bootstrap. We've never understood why. I'm here to tell you that computer science education is one of the most sophisticated engineering problems in existence. It's waiting for someone to step in and do some of the deep, possibly unsexy engineering work to create a solution. At Bootstrap, we've built one of the largest and most diverse CS education programs in the nation, and we did it at a fraction of the cost and with a team of 4 human beings. And we did it because we looked at the problem like engineers working at startup scale. Imagine what a company like Google could do. So I want to leave it there. I'm happy to answer any questions you have. This is an engineering problem that is built for a company like Google. Thank you. Yes.
Do you test the kids? You said let's test it at the end.
Absolutely. Yes, so the question was, do we test the kids? And I'm so glad you asked. That is literally my secret last slide. Whoops. Load. This should be mirroring. Can you guys see my screen here? Great. So the answer is yes. You better believe we test the kids. And in fact, the tests that we use for our initial study all involve questions drawn from national and state standardized tests. Not because we're in love with standardized tests, but because we understand that decision makers want to see that kind of stuff. And what we've seen is statistically significant evidence of fairly large gains on 3 tasks that we've looked at so far: function composition, solving word problems, and matching between representations of functions.
Okay, so this is pre and post. This isn't the kids who got this curriculum versus the kids who got a standard algebra curriculum.
The lower table is that. The upper table is pre and post.
Is that correct?
No, the lower table is demographic distribution. This table right here is showing gains pre-post, not looking at a control group. I will say that this is the first curriculum ever to have demonstrated evidence of transfer. We're gathering additional data. We're building a much larger data set that includes control groups, so we'll be able to compare apples and oranges. But historically, this belief that learning to code will help you in math class has not been true. The simple fact that this table exists was something we're extremely proud of. We've been able to make that happen. Great question. Yeah?
Yeah, similar question. We have a longitudinal study, so like, those people who Bootstrap 4 years afterwards when they go to college, when they actually get a first job.
Unfortunately, maintaining data on minors is extremely complex. I mean, I'm with you. I wish I could stand here and say we've tracked these thousands of kids, we know what happens to them. We don't. What I can say is the schools that have adopted Bootstrap continue to use it. And I mean, it's not hard data. It's proxy and anecdotes at this point, so I can't answer that. Yeah. Yeah.
Can you talk a little bit about your choice of language? Because there's a lot of conversation about what the AP curriculum uses to teach. And I graduated from high school pretty recently, and there was a lot of talk about shifting the fact of teaching object-oriented programming through Java to teaching through Python just because it's more flexible. And if you teach it through an algebra class, it makes sense that you would use something as functional as Lisp or something to make it useful to algebra. But is it still useful outside of that class and in a different context?
So I heard sort of 2 questions in there. So one of them you were saying is sort of how did we choose our language, right? What factors go into it? And the second is functional programming useful outside of a math class?
Not functional programming itself, but the way that you teach it. Does it make sense to students that it would be useful outside of the context of that math class?
Oh, absolutely. Right. In fact, the program by design curriculum that I mentioned is used in universities around the world. They actually use the same language that we're using, and we've borrowed the same design recipe. So a student in Boston can go over to Northeastern University, and they will see, oh my God, the freshman CS majors are doing the same work that we do. And in fact, I don't know if you want to mention this, because this is a parallel in New York as well.
Well, I'm no longer at Adelphi, so Adelphi is no longer using this approach in their CS0 class. But it was for a number of years while I was there. Adelphi University is a mid-level liberal arts school where I was on the CS faculty, and we had a CS0 class, programming for poets, programming for non-majors, and we did it this way. And we had a fair number of students who had such a good time that they became CS majors, and they seem to have learned a lot.
So there are parallels directly into a number of universities around the world, but more importantly than that, yes, functional programming is in a whole bunch of companies as well. It's used in plenty of industrial contexts, so the language itself transfers. But
big data.
Especially big data, that's right. But more significantly, this approach that we're using, the structured problem solving, writing a type specification and thinking through your unit tests deeply before you dive into the code, that's a high-level skill that's relevant no matter what language you're using, right? I mean, I went to the bathroom before giving this talk, and I think Google is famous for your testing on the toilet pages. This is something that is transferable across languages, right? This is where you get the explicit process that transfers everywhere. As far as how do we choose our language, or like why, I think this debate about should we use Python or should we use Java, it needs to be about what is our learning goal. Computer science teachers are the only teachers I can think of any discipline that when you ask them, what do you teach? Their answer is the tool. Imagine if I asked a math teacher, what do you teach? They might say, algebra, geometry, calculus, right? They're not going to say calculator. If I ask a chemistry teacher, what do you teach? Maybe orgo, right? Maybe some physical chemistry. You'd think they were crazy if they answered and said, I teach Bunsen burner. But when you ask your average CS teacher, what do you teach? Their answer is Python, Scratch, Java. It's the only discipline where they self-identify by the tool, and that's the problem. We cannot over-focus on the tool because there's this dependency graph that requires that we think a little more broadly. Other questions?
Yes.
Yeah.
So initially you had said you were an after-school program, and then you made changes for that. And you said you were really large, and then you stopped. And I wanted you to expand on what happened and why. And all
Yeah.
that stuff.
Sure. So we actually partnered with a terrific after-school program called Citizen Schools. They're national in scope. They're very active in New York, and I know Google has done some work with them in the past. They're great. I have huge respect. In fact, I was a Citizen Schools employee at one point. Here's what we noticed when we were doing an after-school programming club. So first, we needed volunteers. So we had to recruit tons of engineers, which is not easy. Second, engineers are busy people, and sometimes life happens, right? You have a ship deadline. The build is broken, so one engineer has to peace out and can't make it that day. So what do? You have redundancy. You recruit 3, 4, or 5 engineers to make sure that at least one of them can be there every single day. So we have to recruit 5 engineers just to teach this after-school program, which is typically how many kids? Maybe 20? Maybe 30? If that.
I've done it, it's like 8.
Yeah. So we're spending all of our time recruiting engineers who need a lot of training to teach, right? You guys are experts at the content, but teaching is hard too. So we're investing a ton in training engineers, 5 engineers to 8 kids. And now, those engineers, once you've trained them, they come back every semester forever, right? They just keep teaching? No? What? Yeah, right, so they get busy, they leave the project. So you have to recruit enormous numbers of volunteers who you lose almost instantly just to reach 20 kids if you're lucky. A single public school math teacher is going to reach 80 to 100 kids in a single year. And if they like what they're doing, if they believe in the program, they'll do it forever until they die or retire, whichever one comes first. Right? So if you're thinking about scale as a priority, after school is amazingly flexible. There's a lot to recommend it, but scale is not one of them. Yeah.
I have 2 questions. One, you're showing like the math learning here. Like, what about, are you measuring the coding learning? Is that a separate metric? Like, how do you know if the program is effective on that dimension?
So, I mean, essentially, we use formative assessment throughout the curriculum. So once we spend about 2 lessons teaching this explicit task, this multi-representational task, the moment that's over, every single thing in the curriculum is a word problem where kids are given a problem statement, a problem to solve, and go. And so we're able to assess as they go through the program, are they able to complete it? Where are they stuck? To be really upfront, the level of programming we teach in our algebra module is fairly small. Right? We're not doing object-oriented programming. We're not doing recursion, for example. But we have an extraordinarily high percentage of students who finish the program, build a video game on their own, and we use that as a proxy for their learning to program. There are some learning studies that we're in the process of doing. The reason we didn't start with those are because for us, we felt that showing math outcomes was the most immediate concern. But we're gathering data and we're looking to report on the CS learning outcomes.
And the other thing I'm curious about, I was a teacher, I taught at Success, which was a charter network, and I think one of the 4 of you perhaps pitched us at some point last year. And I'm just curious, like, what do you think are the biggest factors that lead to schools adopting or not adopting Bootstrap? Or like, are you bottlenecked by just the number of people who work for Bootstrap, or by schools' willingness to try it out, or like, what are sort of some of the factors?
So, I mean, right now, our capacity problem is we do not have enough staff to train teachers fast enough. There are far more teachers who are looking for training than we can train in a year. But as far as the bottleneck at the school, right, what makes a school successful? I mean, I think a significant part of that is the administration needs to believe in the program, because if a math teacher comes to our training, gets excited, and then goes back to the classroom and starts saying, all right, we're going to do this, and the principal looks in the door and says, why are kids making video games? Right? Why are they even on a computer? That principal, justifiably might be hesitant about somebody messing with their math scores. And so often we hear from teachers who are saying, I really want to teach the program. I wasn't able to get the administrative buy-in. So that's a messaging issue for us. There is something of a bottleneck around, look, some schools do not have even enough computers for a once-a-week laptop card. That's starting to dissipate, right? The hardware problem is starting to get solved. But I think that the third most common issue is a sense of teacher support. So this is an area in particular where Google can be enormously instrumental, right? So there's tons of teachers using Bootstrap in New York City public schools right now. I would say a non-trivial percentage of them are thinking to themselves, all right, I'm doing it. It sure would be cool if I could have an engineer just come and visit my class like once or twice, just to like have my back and to talk to my kids, right? That boost, that sense of there could be someone I could call upon, that would be tremendous. Even if that teacher never calls on you, just knowing that they could can be the difference between them teaching it or not teaching it. So I think those are the top 3 bottlenecks.
The last one seems pretty solvable. I bet people would sign up for that.
I hope people would. Yeah.
It is Google Serve Month.
There you go. Oh, is it? Perfect. Yes, sir.
So I did Teach for America, and I taught Algebra 1 for
Awesome.
2 years. So I'm just like trying to put myself in the shoes, and I feel like kind of touched on it just then, but like teacher buy-in is probably something that's very tricky, just because I can see, at least like the teachers in my school, ones that have been there for 30 years, every year there's some new way to teach math, and they're like, listen, I've got it down by now, and they kind of discard it.
Yep.
But like on a bigger scale, like district and kind of federal, where are we? Because eventually you feel like we get to the point where this curriculum would be required, or like it's so like ingrained in our society that we would need to have it on kind of a bigger level. Like where are we in that?
We're not even at the starting line. So in terms of teacher buy-in, that's something that we excel at. I'm a former math teacher, so in our trainings we are math teacher to math teacher. We focus heavily on the math. Typically, we don't mention the computer science learning outcomes because we're there to talk math. And the veteran teachers buy in at a deeper level than the young bucks, because the young teachers are like, finally, computers, cool. They're not necessarily thinking about the math connection. The veteran teachers see it. So we've been fairly successful there, and it took 10 years for us to get to that point, so it's not an easy thing to do. But as far as the federal level goes, it's a hard engineering problem, right? Scale comes not from getting to 10 million kids in your first year. It comes from building up a pool of teachers. Maybe you only train 1,000 teachers a year, but every teacher you train keeps doing it until they die or retire. Right now, the trend in Scale is, how do you get to 10 million kids in year 1? And if that's a threshold, guess what? YouTube videos. We'll do YouTube videos to teach math through programming. Like that, it's quick, it's easy, it's cheap. You don't get the rigor. And you don't get teacher buy-in for that either. I think a lot of governors have made some really terrific proclamations about getting everyone to code, and then it falls to the superintendents in their states to figure out how to make that happen. And what winds up happening is, well, we used to have this class on PowerPoint and Excel. That's kind of like a programming class. Let's have that count as CS. So sometimes we're repurposing an existing class and calling it CS. Or we're doing hour of code. 1 hour a year, every kid does it. We've taught computer science, check. Or we'll take the elective route, which has its benefits, but it also has some drawbacks. So I think in order for there to actually be a policy movement on this, someone needs to tackle the engineering problem and get buy-in and say, we're going to build something scalable, but it's not going to happen in 1 year. And unfortunately, that sales pitch is hard to make when someone else says, I can do it in a year and I can do it for cheap. All I need is a video crew. Yeah.
So what you just said about the issues that you have, I've taught with citizen schools, for several years, and I pretty much agree with everything you said about the issues about how it requires a lot of expensive resources.
Yeah.
It takes a long time to build up, and all of this stuff. So what would you have advice for what people that are interested in doing this type of stuff and actually would like to dedicate some time over the long term like how to approach this type of problem. Like what, for people that aren't going to go and like start or join, Bootstrap or something.
Well, what are your constraints? Are you thinking like career change, or are you
I'm
thinking
like, what would be the type of thing that you could do for a couple hours a week and have a useful and meaningful impact?
So I think this, that kind of thing is where you can be complementary to an after-school organization like Citizen Schools, like After School All-Stars, right? Maybe you personally decide, I'm going to invest in teaching an after-school programming class through one of these programs, but I'm going to be responsible for recruiting and maintaining a rotating community of volunteers, right, of coworkers, and I'm going to make sure that they get trained. And since maybe you've done it 2 or 3 times, maybe you can be the one to train them. If you keep that pathway sustainable, you can start to have a bigger impact. Option 2, connect with an organization like Bootstrap and say, I want to be available for any teacher who has questions. I would love to just be able to work with those teachers, even though I've only got a couple of hours a week. I think there are summer camps that they don't necessarily hit the equity angle all that well, but you can do so much when you have kids for 8 hours a day for 3, 4, 5 weeks. I mean, you can do a lot there without having to give up an entire part-time year.
That's interesting. Thank you.
Yeah. All right. Well, I know our time is up. I know everyone is really curious to hear about the testimony that came out, so I'll leave you guys to it. But thank you so much for having me. Thank you, Google, for all of the technology that we have built our platform on, so we really appreciate it. And thanks especially to my host, Andrew, for setting this up. So.